times of black holes. What are they? How do we know they actually exist and not just ethereal?
Presenting this talk is a University Distinguished Professor of Astronomy and Associate Dean of the College of Science at the University of Arizona. His research interests are observation of cosmology, gravitational lensing, and the evolution and structures of galaxies, using telescopes and other instruments to study the largest scale structures. He has over 108 referred publications, in addition to 70 conference proceedings, and his work has been supported by NASA and the NSF. As a professor, he has won 11 teaching awards and has Professor Chris Impey, thank you so much for being with us tonight.
Yeah, it's a pleasure. It's daytime for me, night, evening for you, and yeah, I'm happy to be with you.
Okay, just a minute so I can mute this person. بس لو سمحت أنت احترم حالك شوي. Okay, guys, one more thing. The talk is going to be 45 minutes. After that, we're going to have a 15-minute Q&A. So for anyone who have any question during this talk, just leave them down in the chat box or send us a message on Instagram. I'm going to send both of the club's Instagram pages, so you could send us a message. And yeah, thank you so much, Professor.
All right, I'll share my screen and then start. Everyone can see that?
Yes.
Okay, so my title, Einstein's Monitors, actually refers to the fact that Einstein himself did not believe that the prediction of his own theory existed, as a number of astrophysicists were in that position early in the last century. So I'm going to talk about the life and times of black holes fairly quickly. You know, it's a big subject, so 45 minutes is not that long. I'll start with a quote from Shakespeare, who apparently anticipated black holes, described them very well in this quote from Macbeth. This is obviously not a real photograph. This is an artist's impression of a black hole. It's a accretion disk surrounding. Along the way, we'll be talking about the two fathers of black holes, Einstein and Stephen Hawking, seen in cartoon form here. And I'm going to just start with the early history, because the idea of black holes was around long before general relativity. It starts with an extrapolation of Newton's law of gravity, and just imagining a situation where an object is either massive or dense enough that the escape velocity equals the velocity of light. So you can see by simple extrapolation of Newtonian gravity, you can compare. So the idea of dark stars was around even at the end of the 18th century. John Michell, a clergyman and amateur astronomer in England, and Laplace, a famous French mathematician, had the idea of dark stars, where they were escape velocity would essentially reach light, and so no information could escape. The reason this idea lapsed for over a century was because around the beginning of the 19th century, Thomas Young demonstrated the wave nature of light. And so the idea of a wave being trapped by gravity did not fit into the physics of the time. And so this idea essentially lapsed. And so we come to Einstein in the beginning of the 20th century. I don't need to say that he was the most famous physicist of his time, perhaps of all time, the only physicist who was a public figure, recognizable to anyone. His life, of course, is full of interesting episodes, but his masterwork was general relativity. So let me talk about why Einstein came up with general relativity, or what he was motivated by. Obviously, I mean, you have some science and astronomy and physics background, but I'm not going to do the physics and to a conceptual level of the subject. Einstein was struck by what seemed to be a coincidence in physics, that the mass, the inertial mass of an object, its resistance to any change in its motion, was identical to its gravitational mass, which is the change in its motion in a situation of gravity. Now, inertial mass has nothing to do. This is really a coincidence that needs an understanding. This coincidence was known from the time of Galileo, but by the time of Einstein, it was measured to be an accurate equivalence, very, very high degree. He used thought experiments, as many theoretical physicists did early in the 20th century and even now. And one pair of situations he realized could not be distinguished was the two you see in the cartoon version here. You could have someone in a rocket being accelerated through space at 9.8 meters per second, and they could drop objects and do simple experiments inside that rocket. Maybe it's a closed situation. They don't know their situation. And to them, that would be indistinguishable from someone in a closed box in a room on the surface of the Earth doing those same experiments. There's no way to distinguish between an acceleration caused by gravity, in the case of someone on the Earth's surface, and acceleration caused by a rocket moving through space, where there's no gravity involved. Doesn't have to be any object nearby. And there's another thought experiment he did, which is you could have a situation where someone's floating freely in a spaceship in deep space, again, far from any object, so gravity is not involved. And they obviously are weightless at this point, and they move around floating in the spaceship. Well, someone on the Earth's surface in a much more ominous situation of an elevator or a lift that the cable is broken and is plunging to the Earth down an elevator shaft, they would be floating around in the elevator, also weightless, feeling no weight, but clearly in a situation of gravity that would be very fatal to them in that situation. Einstein was struck by this coincidence. He actually called this example his happiest thought, which is a rather macabre way of viewing someone who's about to die in an elevator. But these were the thought experiments that led him to a new way of thinking about gravity, because he saw that gravity was really, in the end, no different from changes of motion caused by other forces. So how can you do a theory of gravity based on that? And the mathematical and physical conception he came up with was the idea of curved space-time, where mass or energy, and he showed their equivalent, of course, with E = mc squared. So mass energy, now hyphenated, curved space-time. And in his theory, going against hundreds of years of Newtonian gravity, space and time are connected. To Newton, of course, they were not connected. Space and time were completely distinct, separate, linear, and essentially infinite in his cosmology. So Einstein has this very different conception of gravity as a force. And it's not the same as Newton's idea of a force acting through the vacuum of space instantaneously, which was a strange concept that even he didn't know how to explain. Einstein now has a geometric theory of gravity, and his supposition that mass energy curved space-time has been borne out many times, and here's just one example from Hubble Space Telescope. The little arcs you see, concentric parts of concentric circles around the central cluster of galaxies, represent more distant galaxies, billions of light years away, whose light is being bent and distorted in a lens. And it's directly analogous to an optical lens. Light is distorted, bent, magnified by gravity in this case. And so Einstein's central idea of the curvature of space-time and the fact that mass can bend light has been demonstrated many, many times, literally thousands of times, even just by the Hubble Space Telescope. There are other predictions of general relativity that have also been confirmed. One strong one is that gravity slows down time, that a clock, some clock that we can trust, perhaps an atomic clock, will run slower in stronger gravity than weak gravity. So that's a very clear prediction of general relativity, and it was confirmed over half a century ago. How do you make a black hole? Well, here's how nature does it. Now you notice in this example, black holes do not have to be the remnant of a star crushed to a very high density. In principle, nature can make black holes of any size. You just have to compress matter to the point where the gravitational force or the pull is such that light or any particle or any information cannot escape. But the first black holes to be found were, of course, astronomical objects that result from massive stars as they die. And this is a schematic view of how different stars die. A star like phase, and so the sun will not create a black hole. It just never will have sufficient core density and gravity to create this state. Somewhat more massive stars will also lose some of their mass along the way and die as supernovae and leave behind neutron stars, which is essentially nuclear matter, pure neutron matter. But the largest stars, the most massive, will lose again some of their mass along the way, will die cataclysmically as a supernova, and they can leave behind a black hole. And the minimum mass black hole mass of the sun. So this is the end state of a star after it's exhausted all of its nuclear fuel. And so this was the prediction from stellar evolution back in the 1930s. And then it became up to astronomers to actually detect these states of matter that are left behind when massive stars die. The principles of black holes are actually very simple. The theory is complicated, of course, it's general relativity, but the properties are simple. Black holes really only have a couple of properties. They're defined by their event horizon, which is an information barrier. It's not a physical barrier. It's the boundary between the information that's trapped forever in the black hole, the matter, light, and any information, and the stuff that we can see in the outside universe. And in principle, the black hole also contains a singularity, because the basic theory predicts the cusp, an infinite density cusp of the core, which is obviously not a physically meaningful idea. Black holes are, and black holes' properties are fairly simple. Then they have a mass, they have a size, and because they formed from a spinning star and conserved angular momentum, they would have angular momentum. And in principle, those are the three properties of a black hole, and that's all. The first discovery of a black hole was Cygnus X-1, this brightest X-ray source in the Cygnus constellation, because astronomers realized an isolated black hole would be essentially impossible to detect. There's nothing to betray its existence. It's dark. But most stars are in binary or multiple systems, so astronomers quickly realized that there would be situations where in a binary pair, one of the stars had died and left behind a black hole, while the other star was still living its life. And in that situation, the black hole will pull material onto it from its companion. And that material, cartoon views, of course, animations, is dark still, as a black hole must be. But the surrounding region, caused by intense gravitational energy, is heated to temperatures of hundreds of thousands or a few. The line of a black hole is a binary system emitting intense X-rays, where the mass, just inferred by Kepler's law applied to the binary system, is 3.5 or more times the mass of the sun, and it's a stellar remnant. And at that mass, it must be a black hole. And that was done for Cygnus X-1 in 1969. So several decades after the theory was developed of how stars might die and leave behind a black hole, the first was detected. And since then, only about 50 or 60 examples like this are known. But they're pretty well studied, and they're very reliably instances of stellar mass black holes. And then we come to the work of Stephen Hawking in the 1980s and the 1970s.
Space-time is almost impossible to contemplate because our entire sensory existence is limited to the 3 dimensions of everyday experience.
Holy macaroni!
The easiest way for us to enter Einstein's universe is to imagine space and time to be like a sheet of rubber.
If space-time were empty, the sheet would be flat. But massive bodies like the Earth and Sun will bend the sheet and cause it to be curved.
This curvature is Einstein's concept of gravity. The more mass a star or planet has, the more steeply it bends space-time around it, and so the more gravity it has. Throw something extremely heavy like a collapsing star onto the sheet, and you soon end up with a universe full of holes.
Ow! Watch it, Cody! Yeah! Oops.
As a massive star cools and shrinks, it will curve the space-time around it more and more. Eventually, when it shrinks to a certain critical size, it will quite literally create a black hole in space-time. Things can fall into a black hole, but nothing can get out.
Oh, there's so much I don't know about astrophysics. I wish I read that book by that wheelchair guy.
The most terrifying concept in astrophysics lurks at the bottom of a black hole, the singularity. Everything that has ever fallen into the hole is destroyed at the singularity, crushed into a pinpoint of infinite density and infinite smallness. Even space and time are squelched out of existence. All that remains of the outside universe is a perfect sphere of absolute darkness, a gravitational ghost of the star that died. This sphere is called the event horizon, and it marks the edge of the abyss.
So I should stress that the singularity is a prediction of general relativity, and it's a part of the black hole construct, but it's unphysical. So the singularity, as Hawking realized very clearly, indicates that the theory is incomplete. So his way of putting it was that the black hole, that the theory is incomplete, that we need a superior theory of gravity to fully understand black holes. And that's what people are, of course, working towards right now.
Guten Tag.
Hawking's other contribution, he made several and major contributions, of course, to black hole theory, but his other one was that black holes are not black. He proposed a mechanism whereby essentially taking the energy from the vacuum of space, when particle-antiparticle pairs are spontaneously created from the vacuum, as can happen in the lab, as can happen anywhere, and then disappear again. If that happens near the event horizon, there's a finite chance that one particle of the pair can pass into the event horizon. And if you follow the logic of that, where the energy is being taken essentially from the vacuum, but one of the particles is radiated outwards or escapes, you have a situation where the black hole is both radiating energy, it has a temperature, and it's evaporating, it's losing mass. And so Hawking radiation is the idea that Hawking came up with to understand this. And the prediction, of course, is that black holes have a temperature. So it's another property, very low temperature. So stellar mass black holes temperature of Hawking radiation is 1/1000th of a Kelvin. That's completely undetectable in astronomy, and it may never be detectable. In fact, it's so small. The evaporation rate is also incredibly slow. And so for a stellar mass black hole, the evaporation time is about 10 to the 56 years, along with 56 zeros after it. And that again is impossibly small for astronomers to measure. So Hawking's predictions about black holes, these predictions have not ever been verified. They still stand in black hole theory and people think they're correct, but they've not been experimentally verified. Associated with this work, Hawking also sharpened the view of the information paradox. He wasn't the only person to come up with this idea, but he wrote about it extensively. Black holes essentially have a large amount of entropy or disorder. And the intuitive way of thinking about that is that information, of course, is going into them and being lost. Another way of thinking about it is that the black hole contains a large number of equivalent states, and the number of equivalent microscopic states is the definition of entropy from Boltzmann. This comes because, of course, we don't know what goes into a black hole. You can have a black hole of a certain mass that's made by the crushing together of matter of all different kinds, and the pathways or the roots of that matter into the black hole are hidden once they're in the black hole. Formally, a black hole, the mass of the sun, has the entropy 100 million times larger than the sun itself. So what's the paradox here? The paradox comes from quantum theory and the conflict between gravity and quantum theory, because quantum theory says that information in particle interactions is always preserved, forward and backward in time as well. And yet particle interactions at the event horizon, or as matter falls into the event horizon, seem to be lost. And that's a problem. That's the information paradox. People have come up with various answers to this, not completely solved. It's a very active research field. Probably 100 papers a year, I think, are written on this topic alone. Some ideas are that the information is somehow coded on the event horizon. It's a holographic principle. Another idea is that the correlations that exist between quantum particles near the event horizon somehow get destroyed in a region just beyond it called the firewall. This has not been observed. So again, these theories are just theories. There's no experimental verification of them. So the information paradox still exists as a problem in astrophysics that's being actively explored. The other information or new data that came through the middle part of the century and into the last few decades was the fact that stellar mass black holes are times the mass of the sun, all the way up to 20 billion times the mass of the sun in distant galaxies. And nature apparently knows how to make black holes of all masses. The intermediate mass black holes, the ones between the largest black holes from dead stars, but we found some of them in globular clusters. So pretty much we filled in this entire spectrum. Like I said, there's only some few dozen black holes that are known in the nearby universe from binary systems. And we project a population of about 10 million black holes. And let me just show you the best evidence for any black hole by the orbits stars in the galaxy. This is a visualization of real astronomy data taken by the UCLA group. An analogous project is run out of the Max Planck Institute in Germany. And these are essentially observations of stars very near the galactic center, within a few light weeks or light months of the center of our galaxy. And the rapid motions of these stars, dozens of them actually now, followed day by day, month by month, year by year for a couple of decades now, strongly infer the presence of a supermassive black hole in the galactic center, about 4 million times the mass of the sun. So each of those stars is a test particle measuring the mass, and the mass is inferred by each of those stars. So I would say the evidence for any black hole, including the stellar ones, is best for this mass black hole in our galactic center. This is the black hole with the best evidence for it of all in the universe. For example, we can see stars that approach very close to the black hole. Here's one called S2 that's been monitored for a couple of decades that came very close to the sun, just 100 times the Earth's sun distance a few years ago. And obviously people are hoping to use these stellar orbits not just to measure the mass, that's been done now for a while, but also to look for close passages for stars that might be occulted by the black hole or the event horizon, to test general relativity in new ways, because you're in the regime of strong gravity here. So the hope is we can test general relativity in ways that we have not to date. This is another affirmation of general relativity. This is the precession that's caused by general relativity. The precession of the perihelion of Mercury, of course, was one of the predictions of general relativity. And it was a very subtle effect in our solar system. But in the case of the black hole in the galactic center, this precession is a very strong effect. And this has also been measured in the galactic center. So this is another affirmation of general relativity. So this is a wonderful test bed in our own galaxy for not just for studying a big black hole, but for testing general relativity in ways that we have not so far. Because as you probably know, well, most of the tests of general relativity are in the so-called weak field regime. They're tests where gravity is not actually strong, as it is, of course, in a black hole. This is the black hole that was hitting the front page of the newspapers a couple of years ago in the galaxy M87. So we'll zoom in to this giant elliptical galaxy, and it has a 6 billion solar mass black hole that was imaged in microwaves by the Event Horizon Telescope a few years ago. So this is a spectacular image. My university is part of that collaboration, and one of the telescopes in that array is on Kitt Peak, a mountaintop near me. So a very exciting image. The asymmetry here represents relativistic effects. So we're seeing the shadowing, of course, of the event horizon. We're seeing the hot emission from the accretion disk, and the asymmetry in that brightness is caused by the fact that the motion is nearly relativistic, and so the relativistic boosting in the forward direction and diminishing and dimming in the direction away. And this image has been very well modeled now. So we've also used the illumination of this material around a very massive black hole at a distance of 65 million light years to test general relativity. So again, we're in a regime where we're actually testing general relativity in new ways using these massive black holes. And we are seeing the event horizon. For scale here on the right, you can see the solar system projected. And so we're talking about a black hole whose event horizon size is somewhat larger than the solar system. It's about the distance that the Voyager spacecraft has traveled from the Earth in 40 years. These images are going to be recurring for another set of objects in the near future. It's hard work, and the Event Horizon Telescope may only ever be able to make images of about 6 massive galaxy event horizons, but more are coming in the next year or two. And here is an example in schematic form of how images like this can really tell us quite a lot about black hole physics and about the relativistic astrophysics near a black hole with a massive galaxy. An even more exotic prediction is that light can wrap around a black hole. And so in principle, if you could resolve the black hole surroundings, the photon rings around a black hole, you would see a series of narrow rings, each of which was capturing light from a different direction, and each ring of which was a demagnified image of the entire universe. So this is an extraordinary prospect if we could ever have sufficient resolution to see these different orbital paths of light trapped by the black hole from different directions. And we could spool it out and play it like a movie, capturing the history of the visible universe as seen from a black hole. This is a schematic form of how that information arrives, and you can see the principle here. So there are different nodes of the rings that can be separated, which represent different paths of the photons wrapping around the black hole a number of times. And each of these rings in principle can be resolved. They're at a different distance from the central image. And just see the first 3 rings here. So we're pretty far from being able to do this yet. Event Horizon Telescope is working at its limits, but there are ways that are being envisaged to improve the instrumentation and the resolution, and perhaps do this kind of experiment in the next decade. So this would be the frontier black hole astrophysics, if you like. Meanwhile, we have a good census of supermassive black holes in the universe. As I said, the best evidence for any black hole is the massive black hole in our galactic center. That's quite a modest one, 4 million times the mass of the sun. The black holes can be 1,000 times bigger. M87 is 1,000 times bigger black hole. Since its launch, Hubble Space Telescope has been taking spectra of the nuclei of galaxies. Dropping a slit across the nucleus of a galaxy will show Doppler shift, blue and red, as you see in the colored schematic there. And the amplitude of those Doppler shifts and their proximity to the nucleus give evidence of dark mass or black hole. So this is the basic way we found black holes in other galaxies. And essentially every galaxy has a black hole now. There's been no exceptions to this rule. But most of them are not bright objects. They do not appear to be eating or consuming matter and emitting high energy particles and radiation. And that's possibly because they spend most of their time inactive. They consume material, and then when they're in an active phase, they actually blow out the gas and material near the center of a galaxy. And so they're quiet for a large fraction of their lifetime until that material reaccumulates and they become active again. In terms of their contribution to the universe as a whole, they're interesting objects, they're exotic, they're exciting, but they don't amount to very much in the pie chart of the universe. Here you see the universe is mostly made of dark matter and dark energy, which are both entities that we wish to understand more about. They're still mysterious. And the stuff we're made of, it's about 5% of the universe, normal atoms, baryonic material. And you can see black holes here are 5/1000%. So black holes are 1,000 times less abundant in terms of normal baryonic material than the atoms that we're made of and that all stars and galaxies are made of. So they're obviously a small component of the universe. A very interesting one, but a small one. When we look at a black hole, often we're looking at radio wavelengths. Radio telescopes have been used to find active galaxies and to zoom in on their cores. Of course, we can't take an image like this, so this is again an artist's impression of what the spinning black hole at the center of this radio galaxy would look like. So these big black holes have been found by a mixture of optical, radio, and X-ray methods over the last few decades. And essentially, they are gravitational engines. As I mentioned, only 1% of all galaxies are active, but we think that they all have black holes in them that are inactive for 99% of the time. And the most luminous of these objects are called quasars, where the energy coming out of this dark object, or rather its environment, is incredibly bright. It could be as much as 10 to the 15 solar luminosities. And in terms of efficiency, they're incredibly efficient, these gravitational engines. The sun obviously creates fusion energy with an efficiency of 0.7%. Black holes, in principle, can turn mass into energy with 40% efficiency. The only thing more efficient would be matter-antimatter annihilation. So these are amazing gravitational engines, which is why when they're bright, we can see them all the way across the edge of the visible universe. And this is what a massive black hole looks like. It's hard to intuit these numbers of millions. The most exciting recent evidence in the nature of black holes has come from gravitational waves. And if there were any doubt that black holes exist and are real, gravitational waves from colliding black holes have removed all that doubt. The first detection, of course, was only a few years ago from the LIGO project, the Laser Interferometer Gravitational Observatory. And this is the original signal from detected in 2015. Separated by 7 milliseconds in their arrival time at the two LIGO locations in the United States at Hanford and Livingston. The crescendo caused by the merger of two black holes about 1 billion light years away. This is a new window in the universe, as well as evidence that black holes exist. And we expect when LIGO comes up with increased sensitivity in about a year, that it will be detecting about 1 black hole merger every week. At the moment, there are about 12 or 14 events that have been confirmed. What LIGO is doing is detecting the space-time ripples that are caused by black hole mergers. So this is a prediction of general relativity, of course, gravitational waves, and it was very hard to detect because they're extremely subtle. The change in the 2 arm lengths of the LIGO interferometer seen on the right amount to much smaller than the width of a proton. So that's an incredibly subtle physics experiment. It's the most accurate physics experiment ever. And what it's doing is detecting the space-time ripples or waves, which could be compression waves or rarefaction waves or transverse waves of invisible space-time. So on the left, you see the visualization of that because you can't see space-time, but you can detect changes in it. And with orthogonal arms of the LIGO detector, you can quantify the gravitational wave that passes through the detector, moving at the speed of light from a distant location. Now, if we could see this up close, this is what it would look like with black holes merge. We can't see it up close, and we can't see it by eye. So this is what gravitational waves from a black hole would look like. And this is an astrophysical simulation. And of course, a visualization of gravitational waves. And here are a set of the LIGO binary pairs that have been seen. With many more to come. What about the danger of black holes? We should at least finish with that. This might not work. So I'll address the issue of death by black hole because that comes up in the media and people always ask about that. Indeed, falling into a black hole left behind when a dead star forms would be nasty. A fate worse than death, perhaps. Spaghettification. It will be the stretching of your body at the level of muscles, bones, tissues, individual molecules, just from the tidal forces. But if you scale up a black hole, while the total gravity increases, the tidal force actually goes down. And conceptually, any black hole more than about 1,000 times the mass of the sun, of which there are plenty, there's one at the center of every galaxy, would actually be survivable because the tidal forces would be modest enough that in principle, you could survive it. And so these are potential experiments of the very far future where people could go into a black hole and survive. They, of course, would be unable to convey what they saw inside to anyone outside, as it would be a bizarre episode because as seen from far away, their time would slow down asymptotically. And so it would seem to the distant observer that the person falling into the black hole never actually reached the event horizon. Their light would be gravitational redshifted until it was dark and dim and invisible, and time would slow down for them till they were essentially frozen at the event horizon. But to the person falling in, they would fall in, their clock would run normally, and they would go to an unknown fate, even if they could survive the passage. And before I show this, I'll just say this is this is not an animation or cartoon. This is a full astrophysical simulation using general relativity of what you actually would see if you could fall into a black hole, with the space-time contours are outlined with a grid so you can see what's happening to space-time. There's also the issue of, are we ever going to be able to create this? Do we potentially have the technology to make a black hole with our capabilities rather than letting nature do it? Because in theory, you can make black holes of any size. There's still speculation that there might be primordial black holes left over from the early Big Bang. Actually, most these are microscopic black holes, or very small mass black holes. The very small ones would have evaporated by Hawking radiation before the present time, but there's a slight window for small mass black holes to have survived to the present day universe. Astronomers have not detected primordial black holes, and the limits on them almost exclude them entirely. As for making them ourselves, well, there was speculation, as you probably recall in the media, that the Large Hadron Collider might be able to make a black hole and it would fall to the center of the Earth and eat everything. Well, that was just a scare, because the Large Hadron Collider is orders of magnitude away from creating the conditions, even microscopically, that would correspond to a black hole. And even if it did, if Hawking's theory is right, that black hole might move towards the center of the Earth, but it would evaporate before it had a chance to accrete and grow. And so there's really no danger, even in theory, from black holes that we might make, and we're not able to make them at the moment. So let me finish with the idea of the far future of the universe and the role that black holes will play in it. Because there's a future of the universe after 1 trillion years from now, when all stars will have died and no new stars will be created. There's no material left to make them. Everything is a stellar corpse. White dwarfs for the most part, neutron stars and black holes. And in the future of this universe governed by entropy and dissipation, energy can be extracted from black holes. It's actually a good place to get energy just by sending in and retrieving probes with suitable trajectories. So any future civilization, far future civilization that had lost its starlight and its energy to run itself, could use black holes to run the civilization. Essentially, you're extracting the rotational energy of the black hole because they're all spinning. And that will survive you for a long period of time, up to about 10 to the 50 years. And then you have to use another strategy. All you need in the end for biology is a temperature difference. Normally, it's the hot sun and the cold sky, and the Earth draws down and emits thermal radiation as a byproduct of biology. But in a far future of black holes, where essentially black holes are the last surviving objects, because 10 to the 50 years from now, everything else will have dissipated. Galaxies will have evaporated, solar systems will have evaporated, maybe even normal matter will have decayed. And the last bastions of structure and matter will be the last big black holes, evaporating slowly, according to Hawking radiation. And in that future universe, the microwave sky is slightly warmer than the Hawking radiation from the black holes. So civilizations could, in principle, in the very, very far future, you can see going up to 10 to the 100 years, build Dyson spheres to trap the radiation, to essentially trap the Hawking radiation and live off that. If you do the math, even for a big black hole, it's only about 1,000 watts. It's not very impressive to run a civilization, but I'm sure we'll be efficient in the future. And so that might just be enough. And so that's the somewhat bizarre far future thought that I will leave you with. Okay, thank you very much. I guess I'll take questions.
Okay.
I do have another appointment at 11, so I've got 10 minutes.
Okay. So in these 10 minutes, guys, if any of you have any question, please feel free to unmute yourself and ask your question, or just type it in the chat box. And then meanwhile, I'm gonna take a couple of questions that we got already. So this is a good one. What came first, the galaxy or the black hole? It's like the chicken egg situation.
It's a good question, and it's not yet resolved. Right, every galaxy has a black hole, and they grow coevally. They grow alongside each other. Generally, the black hole is 1,000 times less massive than the galaxy that contains it, so it's a small component. At the moment, the theory is that the black hole actually did form first, because there was probably a first generation of stars called population 3 stars that formed in the early universe within the first 100 million years. And these were stars, of course, that had no heavy elements because they hadn't been created yet. And in the theory of how the first wave of stars formed, they can be quite massive, more massive than stars we see in the nearby universe. And so the prediction is that that first wave of stars in the first 50 to 100 million years of the universe could have formed black holes up to 100 or even 200 times the mass of the sun. And if that happened, then those would be natural seeds for subsequent galaxy formation. So in that idea, stars in the first wave of star formation and galaxies nucleated around them. But it's not resolved. You could equally make a scenario where the small galaxies form first and form small black holes within them. And then we do know that in the later universe, as galaxies grow and merge, the black holes within them grow and merge. So you have a natural way to grow bigger black holes by colliding and merging galaxies too.
Okay, excellent, thank you. Another question is, hypothetically, what if the sun turned into a black hole? Would that affect the orbit of the planets?
Right.
What would happen to us,
No,
basically?
it actually wouldn't. So the sun will not become a black hole. But if some evil alien genius empire crushed the sun to 3 kilometers in size overnight, yes, it would be a black hole. But the gravity at 100, at 150 million kilometers would be unaltered. So you're far from the general relativity regime. So really, we would see no difference. So the Earth would continue completely unaltered in its orbit. The loss of the light, of course, would mean the end of life on Earth. So bad outcome, but not really a gravity outcome, just a radiation outcome.
Okay, great. We got a question. Oh, okay. Does anyone has any question would like to ask?
I see one in the chat about black holes leading to the
Yeah.
universe. So there's a realm of speculation of black holes that involves the idea of white holes. That involves the idea, since a black hole is a fissure, if you like, or a rupture in space-time, that possibly it could connect to other distant locations in space-time. And that's possible. That in gravity theory, that's completely possible. Kip Thorne has written popular books about this, and he's probably one of the best gravity theorists on Earth. And he does not rule out these ideas. Unfortunately, though, the universe seems rather simpler than that. Space-time, if it were corrugated and had interesting topology, then you could imagine interconnected regions and black holes being portals to other parts of space-time. But our universe is actually very flat and boring. I mean, space-time is essentially flat. The black holes are very unusual places where space-time is highly curved. So it doesn't look like white holes exist, or that we have any way of actually detecting them. And at the moment, the idea of them as portals to other parts of space-time is, it can be confirmed, and it's perhaps unlikely.
Okay, thank you. We got another question. I'm not sure it's very clear, so I'm gonna ask it anyway. What rotates in a black hole to have angular momentum? If angular momentum is conserved, where does the momentum of the black hole accretion disk go when it falls to the black hole?
Right, so you can track the angular momentum of a black hole system. So obviously the star, as it collapses, conserves angular momentum, and black holes will be spinning very rapidly because the sun orbits every 24 hours basically, and so something that's collapsed by a factor of 1,000,000 from the sun will be spinning. You can do the math, it's going to spin very fast indeed. And we already have pulsars that spin 1,000 times a second, millisecond pulsars. So we know that stellar collapsed stellar objects have high angular momentum and very high spin rates. The material around a black hole is again subject to the same physics and supported, so they're in stable, mostly matters in stable orbits around the black hole, and it's also puffed up or kept buoyant by radiation pressure because it has very high temperature in that plasma. The inner part of the accretion disk, the inner region of the accretion disk, are orbits where particles can go into the black hole, and that's the path by which matter falls into the black hole. It's actually a very slow rate. So even the big black holes at the centers of galaxies, which are millions or even billions of times the mass of the sun, they're only accreting, which is directly ingesting, about 1 or 2 solar masses a year. So very, very tiny fraction of their total mass is actually going in any given period of time.
Okay, thank you. I'm going to take our last question. It's in the chat box. In your opinion, which theory has the best shot to become the theory of everything?
Well, it's been a long road to try and come up with a theory. What we're really talking about is unifying gravity and quantum theory. That was the quest of Einstein in the last 20 years of his life. He was unsuccessful. It's been the goal of string theory, which has been around for over 40 years, and they've had some successes, but not others. There are alternative gravity theories out there because, as I mentioned, gravity theory is known to be incomplete. It does not resolve issues of quantum theory and the information paradox and so on. And really, it is a very, very hard physics problem. So I'm not even going to say what I think the best bet is. String theory is still under active investigation, but it's proving extremely challenging to derive to decide what the right string theory is, because it's not one thing. Essentially, it's a whole suite of ideas. And alternative gravity theories are also extremely difficult to deal with. You should remember that in the entire century we've had general relativity. If you're trying to calculate the space-time metric, which is the full solution of gravity for an astrophysical situation, there have only ever been 3 space-time metrics calculated. The Ker metric, the Schwarzschild metric, and there was one calculated in the last decade. So that just tells you how incredibly hard it is to work in gravity theory, and that's general relativity. So alternatives are similarly difficult. So I'm afraid this is just an area where progress has been slow because it's an extremely difficult problem, but maybe we'll get there.
Maybe. We hope so. Okay, since it's almost 11, we're going to end it here. So thank you so much, Professor, for being here with us today. And that talk was super interesting, especially with a topic like this. It's really an honor for you, for us. Thank you for everyone who attended, and I hope you enjoyed this talk, and see you next time.
Pleased to be here.
Thank you, Professor.
Good luck. See you. Thanks.
Thank you. Bye-bye.